Hello everyone, so welcome back to part 4 of our R course. This is still working through the basics, they're getting to the end of them I would say. We're going to do logical operators today and some more work on indexing. Here are some exercises to check your understanding from what we've covered in the last few sessions, in particular the last one. You should be able to look at these 2 lines of code and predict what they're going to approximately produce before you run them. So, you want to get off and do that? All right, let's go through them. So what you could have looked at is that this one starts by defining a vector. We know because we've got C, the catenation operator. It's going to define a vector. The elements of the vector are all character elements. We know because of these quote marks. So it's going to be a vector of characters. In fact, we can just run that and we see that there's some English words here. I wonder why, and then some punctuation, comma, full stop question mark. And now what are we doing with that vector? We're running the indexing operator. So we're going to be selecting parts of that vector according to the contents of the indexing operator. And the contents are another vector. And this one is going to be a numerical vector. You can see because these are all values and they get interpreted as numerical. So because they're used as indexes, the index 1 corresponds to the first entry. So the output vector, the first output will be this word I. 2, 3, 4, so the next word will be wonder, the next word will be why. 4, the fourth element is the comma. Now we go back, so the 5th element of the output will be the first element of what's being selected, so it will be I. So we're going to get I wonder why, comma, I, and you could go through and do this. And in the end, what you get is a poem by the late Richard Feynman, absolutely brilliant physicist. Slightly problematic. you can watch a YouTube video by Angela Collier that dives into that wonderfully. That's that one. I hope that worked for you. The second one has a similar format. So we've got something and it's being indexed. That's something. What is it? Starts with a V. Variable. It's like a box that contains something. We know we've come across this variable before. It's a box that contains characters again, and they are the letters of the alphabet. So what are we doing with the indexing in this case? Well, let's break that down. So we've got 2 thingies either side of the, and I've looked this up now, this is actually just called the colon operator, which is a pretty boring name and not very descriptive, but we know that that creates vectors that increment by 1, so it's good for creating series of numbers. And it's going to start at the thing on the left and end at the thing on the right. So the thing on the left, what is that? That is the length of the vector letters. Now letters, it's the alphabet. I hope everything's... You'll trust me that the regular old Latin alphabet that we use has 26 letters, so that's going to be the number 26. And this here, well, first to notice is it's inside brackets. What are brackets there for? Well, one thing we know that they're there for is to define a function. So length is a function, we can tell because it precedes some brackets. The other thing it's there for is to enforce, starts with a P, precedence. Precedence, meaning what operations get done first. So in this case, it's going to look at those brackets and it's going to do that whole operation before it starts looking at other operations like this one here, like the colon operator. So this one is all going to get sorted out first. It's going to go length letters, which you know is 26. It's going to subtract 10, so we're going to have a number lower than 26, 16. And this, therefore, because of the increment operator, is going to go 26, 25, 24, but down to 16. So because they're indices, we're going to start at the index 26, that's going to be the last letter of the alphabet Z, and then it will go backwards Y, X, W, V, etc. In effect, this is how we get the last 10 letters of the alphabet in reverse order. All good? So make sure that all made total sense and that you're very comfortable and have internalized all the logic there, because we're going to take this a step further. So logical indexing, for this part, we are going to need a couple of variables just for didactical purposes. The first one is called V. That is just the letters A, B, C, and D, V for vector. The next one's called L for logical. And that is going to be another vector, you can see, because we used the catenate operator to create it. But it's got these values in it that are of a different class to before. So classes, you remember, we've seen classes, we've seen character classes like this one here, we've seen numeric, we've seen integer, and I have, I believe, covered at least one example of a logical class before. So this is a vector of logical items. And logical items, you know, the class logical basically just contains true and false. There are some other special little things like NA, you know, not applicable. But mostly it's there for storing true and false. Why is that useful? Now, let's run this line of code and see what happens. So you can see I'm taking the vector, I'm indexing it, but it's not like what I've been doing here before, where I've supplied it with something that will eventually resolve to numbers corresponding to the entries. I've given it a logical vector. Okay, so the output has 3 entries. Out of A, B, C, and D, the B is missing, A, C, and D. And you will probably have realized that this corresponds to the entries of the indexing vector that were true. So it went through and it went, okay, let's line up these 2 vectors. The first one says true, so we'll make that A. The second is false, don't include the B then. Next one is true, next one is... This is good, right? This is actually telling you that you should think about this. Behind the scenes, R is actually recognizing, hey, I'm not being indexed by numbers anymore. The indexing operator, you know, it's a program in itself, if you like. And behind the scenes is actually looking at what it's got and saying, okay, Tim's given me a logical vector here. I'm gonna do a different paradigm of operation here. So it does that. We can just check our understanding is good. Just predict the outcome of this. We've got V and then false, 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 true. So not that, not that, not that. Yes, that. False, 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 true. We should just get D, right? And we do, which is good. Now, let's take that one step further. What happens if the thing that we're doing the indexing with is not the same length as the original vector? Now, we've come across this before when we've done operations on vectors of different length. For example, you know, if you a length 4 vector added to a length 2 vector, what happened? Well, the shorter vector generally recycled. So it lined up the first 2 elements, and then when it tried to line up the next 2, it said, oh, one of these vectors is too short, except I'll just go back to the start of that vector. That's exactly what happens here. The most simple example, as we've discussed, of recycling is when you just have a single element. So for every single letter of the alphabet, it's going to, well, assuming that indexing operators recycle, just like, you know, addition and subtraction and other operators like that, we should get all the letters of the alphabet. So, yep, that suggests that there is a recycling function. What about if we give it true, false? If it's recycling that, then it's going to go A true, B false, C. It's going to look at the indexing vector and go, oh, it's only length 2. What do I do now? Go back to the start. So it's going to be C true, D false, E true, F false. We'll get every second letter of the alphabet. Is that what we get? Yeah. So it does recycling. Now, previously, we saw interesting behavior when the recycled vector, the shorter vector, did not fit evenly. It wasn't recycled wholly a certain number of times. What's going to happen with the alphabet? Because here that was fine. 26, 2 goes into 26 13 times. But 3 doesn't go into 26, does it? Because 3 7s are 21, and then you get 24, and yeah. So it doesn't go into 26. So what is it gonna do? Previously, we've seen things like throwing errors, throwing warnings. In this case, nothing. It just goes right ahead, and it gives us every 3rd element of the alphabet. This is a bit of a hack, actually. I've written here that index recycling does not insist upon the lengths being multiples. Exactly what happens. This is a bit of a hack. It's a very cool trick that can be used to great effect occasionally. I sometimes use it when I'm manually plotting lines. I would disagree with the decisions by whoever developed this bit of code. I would throw a warning here and say this looks like a mistake, because it does, and it should. It should be something you're cautious about. But yep, you need to know the behavior of your very fundamentals of R, to master it. So that's why we do this kind of stuff. All right. Layered 1 concept. Let's start layering more. Now, we've done assignment before. When we first covered variables, it's taking objects and putting them into labeled boxes, such as letters, letters is the label of a box that contains all the letters. And we know that now we can select, for example, every 3rd element of letters. What happens if we combine that with this assignment operator, the operator that wants to shove things in? Is this going to actually sort of select out every third element, and then in that third element, shove the value hello. Well, we can run it. It doesn't throw any warnings or errors. Let's look what it's done. Exactly, did that. So this is brilliant as well, right? Because R is actually, behind the scenes, this is a different, assignment indexing is a separate function to just indexing or just assignment. It combines the behavior of both, but secretly, you should see this as a different function. So it's referring to the spots in memory that contain the values that are every third letter of the alphabet, and it's saying replace those values with this representation of this character string, which is great. Okay, so this here refers to a vector that is a certain length, right? So if we try to do assignment with something of a different length, again, we're going back to this idea of different length things. So, there are going to be rules about recycling. Is it going to allow us to, first, is it going to recycle at all? Secondly, are the rules going to be that it has to recycle perfectly? Is it going to give us a warning or an error? Let's find out. So here's every third element. I think that's 9. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. I recorded this video yesterday. It got deleted. I had a meltdown, a minor meltdown. And so yep, I know some of these things. I've been through this a few times. So we try to replace 9 elements with 2, right? 2, if the universe is all in order, will not go into 9. So what do we get? We get a warning, okay? We got a warning, but it has actually done it. And what do we expect it to have done? Well, we've got every third element. So A, B, C, D, E, F, G, H, I. Got a rhythmic sort of a waltz over the vector, if you like. And we're going to replace it with 2 items. So I reckon it's going to go hello, 2, 3, goodbye, 2, 3, hello, 2, 3, goodbye, 2, 3. Sorry, you can figure out why I did that. So hello, 2, 3, goodbye, 2, 3, hello, goodbye. Fascinating, right? It's a very simple line of code. Actually, a lot more into it when you spell it out. A lot more going on. Go ahead and try to predict what this is going to do. Take a sec. I won't talk through it. We've done the concepts that you need to understand this already. But why did it throw the warning? Ask yourself. Very good. The answer, by the way, is that this has 13 elements, and 13 doesn't go into 2. Cool. So, and this one here, this is where we take out those. So we're going to get 13 elements again, and we're going to try and replace them with 3. So I reckon that's going to give us a warning as well. No? True, false, false. I'm so sorry. 13, Tim. 9. 9 elements, 9 goes into 3, so we don't get a warning, and we end up with that. Cool. Make sure you take yourself through that and try to get less confused than I just did then. Got it? Now we're going to go on to something that is going to tie the point of this logical indexing and just burn it onto reality. And you'll see why it's incredibly powerful, especially for managing data. So we need a new concept here. Just turn your brains off from everything you just learned for a sec. Think afresh. Ready? We're going to do logical operations. Now, I'm doing a vector assignment here. I'm going to take V. I know I've used that letter before, so it's going to overwrite whatever's in there. It's going to assign into it the numbers from -3 through to 3. Okay, let's just have a quick look inside there and make sure that all worked. Good. Now I'm going to ask a question about my vector. This is the essence of logical operations. They are the way you ask questions of your data, and it's usually your vectors. So I'm going to ask the question, V greater than 0? You could imagine, I'll put it as a comment, that there's a question mark after this, which is how you should imagine it. And what's it going to do? It's going to take each element of V and ask the question, are you greater than 0? And we're going to get back a logical vector. Logical operation, right? So it's going to say, no, -3 is not greater than 0. No, that's not. No, that's not. No, that's not. But these 3 are. So false, 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 true, true, true. Similarly, less than 0, you can predict the output of this. Great. The double equals sign is how we ask, is it equal to 0? It's different because equals, the symbol equals, as I told you before, and you should not do this, can be used as an assignment operator. It can be used as an equivalent to the arrow dash. Do not do that. It creates ambiguity, and it's only in there because, I don't know, people would riot in the streets if it weren't that way, because other programming languages use equals in that way. But in programming, across most major languages, I think the operation of asking a logical question, is this equal to 0, is a double equals symbol. So you should get the true sitting in the middle at the only value that is in fact 0. What's going on here? This is not equals. In programming, the bang, and we call that's an exclamation mark normally to most people, but programmers have this hilarious habit of renaming characters with different names. So we call that a bang. This one's my favorite one. Is this starts a lot of Unix programs. That's called the interrobang because it's interrogating with a question mark. And yeah. Listen, I have ADHD. So if you have, if you write the bang, it tends to negate things and says not. So if we go not and equals, it's the not equals. So every element that's not equal to 1 should get a true, and it absolutely does. So let's go ahead and apply some of these principles. So here's, or show you how these principles can be applied to a real data problem. Here is an example to remind us of the fact that if we have a vector like v, we can chuck in some logical sequence there that can be used as inside an indexing operator to select it. So this one says false, true, false, true, false, true. So we're going to get every second item back. All right. So remember that. Now, I can create these strings of falses and trues by asking questions of the vector. For example, is v greater than 0? So why don't I take the result of that, my false trues, and put it in v? And what am I going to get back? I'm going to have filtered. This is fundamental to data science, is being able to effectively describe to the program how you want to filter data. And in this case, I've just shown you the way, or at least one of the most fundamental rudimentary ways that you can filter data in R. You can ask logical questions and use them in the indexing operator. That is why all of this stuff, the ability to use logical vectors in indexing, that's why all of that exists. Okay, let's try something just to give you a tiny taste of how far this can go, and it can go incredibly far. You can be amazingly loquacious and descriptive using logical operators. But I'm going to say v is not equal to the maximum of all the elements in v. Okay, so the maximum of all the elements in v is the biggest one. It's a 3, and I'm going to create a vector that asks, hey, what are the elements of v that are not equal to that? It's going to go true, 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 false, because all the elements are not equal to the max of v thing. When you're reading this code, there's some recycling going on there. Did you pick that? If that sounds like gobbledygook and I'm moving too quickly, then just pause and have a think. Why did Tim say that there's recycling going on in this part of the command? Okay. It's because max v produces one element and v produces a number of elements, so they're of different lengths, so one of them has to recycle. Okay, and now we're going to use that logical vector that describes which elements are not the biggest one on v, and we have that would be, this is like Windsorizing your data set, right? Saying get rid of the really big values or something like that, or get rid of the biggest value. That's absolutely something you do in data science in some context, presumably. Sure, I've done it. Okay, good. Let us go forward to combined logical operations. We're just going to get more complicated with logic and learn a few more tricks. To demonstrate this, here we go, some didactical vectors. TTF for true, true, false, because that's what's in it. FTF for false, true, false. Now, I'm going to use the AND operator. Logic is wonderful because it follows the conventions of natural language extremely well. Sorry, I'm just checking the recording's still going because, as I said, last time it failed after half an hour of recording and I was an unhappy fellow. So, so this is going to do an AND operation. The result is false, true, false. Why is that? Because AND is asking, is it true that the fellow on the left is true and the fellow on the right is true at the same time. So it's taking these fellows on the left, the fellows on the right. It's a vectorized operation, so it does them element-wise. Remember your vocabulary. It does them element-wise, which means that it compares the first two lines up vectors and asks, is this one true and that one true? The answer is, of course, no, so you get a false as a result. Is this one true and is that one true? So the second element of the output is true because they are both true. Is this true and that true? Well, that fails in both counts. So that's obviously false. That's why you get that answer. So now you can use the fact that you are familiar with the concept of OR from just the fact that you presumably speak English if you're watching this video in this language. And you can ask, why does this do that? So this one, again, it's asking OR. Is at least one of them true? So in this case, that's going to be true. In this case, it's going to be true. In this case, it's going to be false. True, true, false. Exactly. Exclusive OR, right? Exclusive OR is the one where, it's a bit awkward in English if I say, if you take the car to the car wash or eat a banana, could you send me a text message? And it wouldn't be that clear what do you do if you eat a banana and go to the car wash? Because, what are you going to do in the car wash? You'd probably eat a banana. So just because it's an ambiguity of the language, we suggest this idea that it should just be one or the other, and it's not clear. When you mean both, it just feels a bit awkward. So the exclusive OR is one that explicitly says it has to be the case that one of these two things is true and not both. So what's going to change here is that when we get true and false, yes, one of them is true. So exclusive OR will say, yep, cool. When it's the case that both of them are true, it's an exclusive OR. So it will say, no, I was looking for cases where one is true. Now you've given me both is true, so I'm going to give you back false. That is not an exclusive OR relationship. Unfortunately, we don't have these. Here's another bit of vocabulary for you. We'll use this later when we start designing them ourselves. This is called an infix operator, is one that goes in between its two arguments. For convenience of notation, things like assignment operators, logical operators, arithmetic operators, they're done as infixes. This is functional notation. These are equivalent. Behind the scenes, one just converts immediately to the other. But yeah, so unfortunately, there's no infix operation to do exclusive OR, so we have to do it in functional notation, and we do get the true, false, false as we described. Okay, the next one includes this bang operator again, and as we said, the bang operator generally means something along the lines of not. So what happens when we apply that to a logical vector? Well, it's going to just do the thing where it reverses the truth values. True becomes false, false becomes true, and it's one of those things, like a guilty person, and you ask, were you at the White House on the night of November the 8th? And they say, well, I wasn't not away from anywhere other than the White, and they're just reversing the truth values as many times as they can by effectively using a whole lot of verbal not operators. So this one will take not true, true, false, will give me false, false, true, and it does. Challenge yourself to come up with this one. Give you a sec just to pause and do it. Okay, let's work through it. So we've got a true, true, false there, and we've got an and then we've got not false, true, false. So what that's going to be is a TTF, and then because we've done the not, we're going to get a TFT. It's going to reverse the trues and the falses. And now we've got an and relationship, so it's going to have to be that each element are they both true? So true, true that will be true. True, false is going to yield false. False, true is going to yield false, true is going to yield false. So we're going to get true, false, false. Haha. Okay, let's keep plugging away, just building our security and our instincts for these things. We're doing this thing again where we take V and then we create a logical vector that's going to be the same length as V and ask questions about V, so we're effectively filtering it. Except now the question we're going to ask is going to be something a bit more sophisticated. So, V greater than equal to 1 and V not equal to 2. You see how this reflects natural language? Can you give me items where V, it's either 1 or bigger but it's not equal to 2, right? So there you go. It's actually quite a natural way to write even though it's obscured by being in code, but once you understand it, you can ask yourself questions about precedence here. Which operation is it going to do first? I can tell you that it's these ones have precedence over the AND operator. So it'll actually do these two first, but you can mess around and ask yourself, how would I test that? What might the results be if the precedents were different? Mentally play around. Come on, it's the best way to learn. V greater than or equal to 1 is going to give us a vector where just these tail elements, where the values are big, and v not equal to 2 is going to give us all elements except false, and then the AND operator is going to say where are these both true. So we're going to get false, 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 true, false, true. Hope that made sense. So, but in the end, we do get all the elements that are bigger than 1, so bigger than or equal to 1, and then it cuts out the element 2. So we just talked about precedence a little bit, and sometimes with logical statements, it's very common that you will actually have to think about precedence. So in this case, the first thing we're going to do is select elements where v is bigger than or equal to 1 and not equal to 2, exactly as we did previously. But then we want to say, we want to make an exception, say or this. So it's either the case that it's bigger than 1, not equal to 2, or we also want to include -1. So we're going to have to do all this first and get our vector that looks like that, where we've got 1 and 3 selected, the values 1 and 3 in the vector, selected by these elements of the logical indexing vector. This stuff drains your brain to teach, man. And then we've got this OR relationship with another vector that is going to be, it's just going to be true when it's equal to -1. So we're doing this ORed with that. This vector is ORed with that, so we're going to get the ultimate vector is going to be true whenever either of these is true. And it can be both because it's not exclusive OR. Do you understand why? Think about it if you don't immediately get it. Okay, so in the end we get something. It's honestly, like when we're doing what I'm doing today and delving into the logic of it and spelling it out, it actually sounds more complicated than the glorious fact that this is really close to natural language. So when you learn to just read this quite intuitively, then you just say it in natural language and the logic starts to flow much more easily. Okay, so if you followed all that so far, then the last two examples will be a way of kind of just winding down and adding two reasonably easy to understand concepts to what we know so far and really rounding out this topic of indexing and logical operations. So first we're going to do the which function, and this is how you jump between the two paradigms of indexing that we've seen so far. So the one is where you give it numbers and the numbers correspond to elements of the vector that you're choosing, and the other is where you give it those logical vectors and it uses them to select the elements. To do it, we'll just first define a vector called v, and we're going to define it using the function rnorm that creates normally distributed random numbers, and by default they have a mean of 0 and a standard deviation of 1. So we create v. You notice that printed to the screen when I clicked that? I didn't have to write v and print it. It just went straight to the screen. The reason is these brackets. It's a party trick. It's a hack. It's just a cutesy little feature of R that if you surround an assignment in brackets, then it will print what are the signs. It's useful, but it's a party trick. Once we've got v, you can ask yourself what this is going to do. I think you'll probably have the answer at hand. It's going to select all the elements of v that are greater than 0. Now, we could have created a numeric vector to do the same selection, right? As in, we could have said that this one, the first element's greater than 0, the second element's greater than 0, the third element is not greater than 0. So we could have created a vector that said 1, 2, it wouldn't have 3 in it because we don't want that. 4, not 5, 6, not 7, 8, not 9, 10, 11, 12, not 13, not 14. You know, so we create a numeric vector to do this. And it would be essentially as though we'd looked at, you know, what we're mentally doing is we're actually almost converting that into a true-false vector, asking this question, is v greater than 0? So we're sort of mentally creating this vector, and then we're giving you the numbers of all the positions that are true. That's what which does. So it just tells you it's the first, the second, the fourth, the sixth, and that. So when you index, you can equivalently run this, or a more verbose version would be to run this, but it does come up very useful in times, especially when you've got extremely long vectors. Think about yourself as a data scientist, maybe a bioinformatician. You're working on something with billions of elements, and very few of them are true. So do you want to store a vector that has all of those billions and it's about a megabyte or something, or 10 megabytes or something on your system, and it has to be read through or stored in memory and just clog everything up? Or do you, if only 6 of them are true, do you just want to store those 6 positions? And that's for example a big data case when which makes a lot more sense. So final thing, this one's really easy. Okay. Sum, we've seen sum before. It just adds up numbers. Sum of 1 to 4 is 1 plus 2 plus 3 plus 4 is 10. Now, we already saw that the indexing operator, it knows what you've given it. It knows whether you've given it a numeric value or a logical vector. A numeric vector or a logical vector. Similarly with sum. So this is the idea here is first is just to teach you a trick in R, but also to raise your consciousness to the fact that R is always, it's modifying its functions. In fact, it's actually behind the scenes, it's doing a thing called dispatching, where it's actually referring to a different function that does kind of the same thing, so they get the same name, but it's actually pulling out the function appropriate to what you gave it. This is a fundamental principle in something called object-oriented programming, and R is an object-oriented programming language. So sum, we know it works on numeric things and it adds them together, but what does it do if we give it something totally different? We give it a logical vector. Well, again, it does something that makes kind of sense, right? It actually just counts the truths, so we're going to get 3 out of this. And very often when we're doing data science problems, we want to know how much of our data set has a certain property. So it's very frequent, for example, in my work in agricultural science, that I just might want to know the threshold for a particular grain sample being accepted by the wheat market operator as of a certain quality. What proportion or how many of our 1,000 samples are exceeding that amount, and I'll do something like I'll take the vector v of that has the values of the wheat quality measurements and ask, are they above this amount? And then I'll ask, so to create some true false vector, and then I'll ask what's the sum of that, and I get my answer. It's 14 samples in this case. So sum on a logical operator adds all the truths. I'm Dr. Mark Timothy Rabanus-Wallace. I'm very grateful to the University of Melbourne for supporting me while I do this, and I look forward to seeing you in the next one, in which we start working with some real data.